we are learning two kinds of equations that we're going to solve today. There's two different kinds. This is the first kind. We already did. Okay, so there's two kinds of equations, and then we're going to kind of do two things with both types. One of them is purely a visualization. It's just meant to hopefully give you a little bit of an understanding of why the solutions work out the way they do. A big part of what we're doing today is interpreting your solution. You're going to do all this algebra and you're going to have a bunch of stuff written in front of you, and then you have to decide, where's the solution? What does this look like? And there's all different kinds of possibilities for both types of questions that we're doing. So the visual that we're doing, don't get caught up on it. Some of you might really like it. Some of you might really get it. But I don't know that it's going to help you solve the problems moving forward. It is, for the most part, an algebraic solution. But what I'm hoping you get from the visual is just that, why these solutions work out the way they do and how they work out differently. And so that will help you interpret your solutions. So if you remember from last week on Thursday, I believe, we did, this is the type that we did here. Okay, where you have an absolute value graph equal to a constant. So this one's like x minus 2 plus 1 equals 5. The absolute value of x minus 2 plus 1 equals 5. So solving that absolute value equation. And it would give us two solutions where those two graphs cross. And then I showed you, I think, an example of one where you might get no solutions as well. Okay, it's possible to have no solutions in these, and we looked briefly at what that would look like algebraically. What's the other possibility? You could have two, you could have none. Anybody see what could happen? Yeah, you could have one if the line was just touching the vertex there. You could have one. These aren't very interesting when you have a single absolute value equal to a constant. It would probably, like, it wouldn't be a surprise that you would end up with one. It would be like when the absolute value of x minus 2 equals 0. That's when you're going to get it. Or x minus 2 plus 1 equals 1. Or plus 2 equals 2. Like, those wouldn't be very interesting. But it's possible. Here are all of the different, for the first type of question that we're doing, remember that was when if I had something like this was last week, equal to a constant, which is a flat horizontal line graphically. This is absolute value equal to a line, like a line, y equals mx plus b kind of a line. That's what that is. So what are the different possible outcomes here? Well, you could have two solutions, right? If the line crosses through here and crosses through in another spot, we see it has something to do with the slope of the line versus the slope of the absolute value lines, because you could think about their steepness as well. What are the other possibilities? Anybody see them in their head, what they might be? It would be great if we could do an activity where you tried to draw them out yourself, but we just don't have time. No? What about this? One solution? Does that make sense? You could have one solution. So again, this would be two solutions because the red line is less steep and cuts through. But if the red line is steeper, it might cut through in one spot and then it wouldn't touch that again. Or even if the red line was parallel to the green line, it would cut through once and then not touch it again. Is that right? Anybody now starting to think of? Yeah, yes, that could happen. It would look similar to this one, I think. It would be a little bit different maybe, but yeah, you could have one solution in different ways for sure. You could certainly have no solution. I believe that's this one. So if the line is less steep and passes below or above the absolute value. Anybody think of what the last one is? It's pretty interesting. You could have infinite solutions if it's the same slope and joins up with that side of the absolute value along the way kind of thing. Exactly. This would be infinite solutions, but it would be, in this case, x greater than or equal to 2. So those are the possible outcomes when you're doing this type, a single absolute value equal to a line. Okay. Now, let's get into this. We are going to graph one of these. So I'm going to graph x minus 2, and I'm going to do it the way we were doing last week, where I'm kind of thinking about them as separate bars, because when I do the algebra, that's what we end up doing. So x minus 2 would be something like this. I'm doing just the dotted lines first, and then the mirror image of that. So this is x minus 2, and then this one, that wasn't a very good line, sorry, is negative x minus 2. Negative x plus 2. Is everybody okay with that? And so that means our graph is this line until it goes there, and then we use the negative of it, and that line afterwards. I'm going to try to draw that a bit better. There we go. That's a little bit better. And so this graph is the absolute value of x minus 2, the blue one. And then finally, I'm going to graph this other one. And I'm just going to do it kind of rough, but 2x minus 1. So I go down to negative 1, and I go up 2 over 1, up 2 over 1, up 2 over 1, down 2 over 1, and I graph that line. So where does my red line, which is 2x minus 1, cross? Like, how many times does it cross the absolute value? Once. So algebraically, we should get one solution. Is everybody okay with this so far? You're not going to be solving by graphing. The visual is just supposed to help our understanding is what you need to be able to do after today. And there's a couple of different types. There's this type of question, and there's another type of question that's coming up. That's very different. Any questions? So when x, this is what we did last week, when x minus 2 is less than 0, which is when x is less than 2, we use the negative of x minus 2 equals 2x minus 1, and we solve this equation. Right? Remember this? So negative x plus 2 equals 2x minus 1. So I'm going to move the 2x over, and I get negative 3x. And I'm going to move the negative, or the 2 over, and I get negative 3, and x equals 1. And what did I notice? That's this answer right here, isn't it? When x equals 1, they cross. And it crossed that bar, didn't it? That side of the graph. Like the algebra matches that. Okay, good. Very quickly, we'll do the other one. When x minus 2 is greater than or equal to 0, which happens when x is greater than or equal to 2. This is case number 2. I just use the regular one. X minus 2 equals 2x minus 1. So I'm going to bring the 2x over, subtract it. I get negative x, and bring the negative 2 over and add it, equals 1 when x equals negative 1. A solution. So how do we interpret this? Do we have two answers? Zach, what do you think? So this is not in the domain that we've set up. But why does it work out as a solution? Look, it's where it crossed this side, if I continued it down, is right there, -1. Like there's the solution, right? So we can see visually why this is giving me an answer, but it's down here, which is not part of the actual graph of the absolute value of x minus 2. But it does cross the line x minus 2. So algebraically, I'm going to get a solution. But this is why we have to understand our domain and where we're using this half of the graph and where we're using this half of the graph so that we know if our solutions matter. When you're doing the algebra, I don't know that you need to think about the graph and which side of the graph you're on. Like that's not the point of this, I don't think. Some of you might, I don't know. But to me, it's just a reminder that not all solutions, like you need a real strong reminder that not all solutions are gonna be good. Okay? So this one doesn't work, so I'm going to put a little x. It's not in the domain. I'm going to say extraneous. Oh, shoot. I've got my thing on. Extraneous. It's not in the domain. Therefore, and I think it's a really good idea to just get in the habit of restating your solution at the end. But this one is good, because x equals 1 is in the domain of x less than 2. Like one of my solutions was fine, the other one wasn't. This could not have really happened last week when it's equal to a constant. You don't get this happening. You don't get this weird, you either get 2 solutions or none, basically. You can't get 1, but it's different. Okay? Any questions about that? So this is similar to what we did in that you split it up into 2 cases, but you really have to consider your solution, and I think we talked about that, how that's going to come up where you really have to. And the thing is, where I already showed you all the different possible outcomes. You could have 1, you could have 2, you could have none, you could have infinite. Like what does that look like algebraically? How do I interpret that? So you have to understand each of these interpretations as you go through and what they mean. That's a big part of what you're doing today and sort of tomorrow and that sort of thing. All right, let's try another one. The mistake some people make is they don't interpret their solution or they don't interpret it properly. The algebra for these ones is pretty straightforward. The other ones we're going to do today are a little bit different, a little bit trickier. But we always start with when 4 minus x, so the argument of the absolute value. I think I used this word last week, but it's probably a little bit new to you in that use. But an argument of something in mathematics is kind of like the radicand of a radical. So whatever's under the radical. Okay, but we use the word argument for other things. So the argument of this absolute value is what's inside the absolute value. That's what I mean by that. So when that is less than 0, and you can solve this however you want. I can move the x over, but I'm going to leave the x where it is and move the 4 over. So when x is less than -4, but what do I do when I multiply by a -1? I got to flip the sign. So this occurs when x is greater than +4. When x is greater than +4, I'm using the negative because I started with the case where the argument is less than 0. And I'm going to solve that equation. And when 4 minus x is greater than or equal to 0, which is when negative x is greater than or equal to -4, which is when x is less than or equal to +4, I'm going to solve this equation. Okay, we'll do this quickly. So my one solution here, when x equals -2, but that's in the case where x is greater than 4. Not true. So it's not in the domain. So it's extraneous. 1 is less than or equal to 4, so that one's fine. Therefore, x equals 1 is our solution. Yep.
Yeah, I'm a little confused how the first one is.
Because this is, you don't look to that. You're looking at that line. When x is greater than 4 is when this will be less than 0. So then I'm using this case. But this, x equals -2, is not in that domain. That's when x is greater than 4. -2 is less than 4. Doesn't match. That's what we mean by, and that's the nice part, is that's always the case. That's how you're checking your answers and considering your solution, is by looking at the domain that you've set yourself up for here. And you could easily do a left side, right side check for these. If I put -2 in over here, I get -6. If I put -2 over here, I get 4 plus 2, which is 6. So this is +6 and this is -6. So like left side does not equal right side. That solution doesn't work. I suppose that's the other way you could check your solutions, is you could plug them into the equation and see if it works. Remember what we're doing. We're finding values of x that make the equation true. And this one doesn't. And what about 1? 4 minus 1 is 3. 3 times 1 is 3. Works fine. Pretty simple. Any questions about that? That was the first type of question that we were doing. This is the second type. We have a whole bunch of these. We're going to do as many as we can. And again, along the way, I'm going to show you the visual of them. The way these work out, the graphs can be kind of confusing. So again, I don't want you to overthink it. I don't understand why that graph looks that way. Don't worry too much about that. I will talk a bit about it, but if you don't get it, it's okay. More what I'm interested in is that you get a sense of why these solutions, how they can be different and why they kind of work out the way they work out. I hope that makes sense. So when we can do this in different ways. This is the thing. I could think about this as an individual function, the graph of it, and adding it to that. So here are those two individual functions. The orange one, is the absolute value of x plus 2, and the purple one is the absolute value of x minus 3. So when I add those together, when does that equal 15? That's one way of thinking about this. The other way of thinking about it is, what would the graph of that function on the whole left side look like? And when does that equal 15? We'll take a look at that in a minute. Before we do that, I'm going to show you how to solve it. These ones are very different. If nobody ever showed you how to solve one of these, I don't think it's not the kind of thing that would be kind of easy to muddle your way through. You need to see it a few times. You need to practice it a bunch of times. You need to know the system for this. Okay, you're not going to just figure it out on the test, which I believe will be Monday, by the way. Okay, just to throw that out there. Okay, here's what you do. You take your two absolute values and you go x plus 2 and x minus 3. And beside them, and kind of below, I'm going to draw a little number line. What are the values that, if I thought of these as x-intercepts, and by the way, if you think about the graph, they are an x-intercept, because look, there's the x-intercept of the graph of x, the absolute value of x minus 3. So this is a lot like polynomials that we were doing. right? If it was like this, x plus 2, x minus 3, what would the x-intercepts be? Do you follow me here? Is everybody okay with this? This is kind of an important part of it. So what's the x-intercept of that one? -2, thank you. You're going to start with that one. You need to have these in the right place. And then the x-intercept of this one? +3, thank you. So we draw out our number line. For values in this section of the number line, like -3, -4, -5, both of these will be less than 0. -5 plus 2 is negative. -5 minus 3 is negative. So both of them will be negative here. Pick a value in this interval, like 0. How about that? 0 plus 2 is positive. So that one I'm going to leave alone. 0 minus 3 is negative. So that one's still negative. And then in this interval, pick a number like 5. 5 plus 2 is positive. 5 minus 3 is still positive. What I'm doing here is I'm outlining my cases like this, but because there's two of them, it's different. But I'm trying to figure this out. The problem is because I have two absolute values, there's three cases. When both of them are negative, when one's negative but one's positive, and when both are positive. And then I'm going to set up these solutions. So then I'm going to summarize by doing this. When x is less than -2, this is when -2 is less than or equal to x, which is less than 3. And this one is when x is greater than or equal to 3. Those are my three cases. In the case where x is less than -2, both my absolute values will be negative. So I've got negative x plus 2 minus x minus 3 equals 15. In the middle case, x plus 2 is positive, so I leave it alone. But x minus 3 is negative, so I multiply it by -1, and I solve that equation. And the last one, they're both positive. And just let's stop. Whoa, I'm really running out of space here. Let's just stop. And this is the problem with these. They take up a lot of space this way and this way because we're kind of drawing pictures and doing all kinds of stuff. I'm going to rewrite what the actual equation was. Plus, yes, x minus 3. So think about what we've done here. When both of these are going to be negative, is this case, I multiplied them both by -1. Absolute value signs are gone. Now I just have brackets. Obviously, you need the brackets because you're distributing the negative. But in this case, one of them was negative, but one of them was positive. So I'm leaving that one alone. I'm only multiplying that one by a negative from my original equation. And in this case, they're both positive. So they're both just left alone. Okay, and we'll quickly solve them. So this is -2x equals 14, x equals -7. X minus x is 0x. And then 2 plus 3 is 5. Subtracting 5 equals 10. So 0 equals 10, which this is never true, obviously. X plus x is 2x. 2 minus 3 is -1, so I'm adding 1. So I've got 16, and x equals 8. Now we have to check our solutions, consider them. X equals -7. Is it in this domain? So that one's fine. This one's never true, so that's obviously not a solution here. And x equals 8, is that greater than or equal to 3? Yes, so this one's fine. Therefore, this one has 2 solutions. And let me show you graphically what that looks like. Here's the actual graph of those functions being added. So the purple line plus the orange line. And if the orange is 0, you can see that it's just purple, right? It's hard to understand, not that hard, sorry, but it would take a little bit of time for us to understand exactly why it looks that way. But these double absolute values, they can look all kinds of funky ways. And this is one of them, and you can just see that there's 2 solutions, and it's +8 and -7. Like, graphically, you can see that. But if you're thinking ahead, this might give you an indication as to there could be some strange solutions happening. Like if this wasn't 15, but it was some other number, what would be happening here? Where would those 2 lines cross? Okay, let's try the next one. Okay, so we start with our number line. My x-intercepts here are -1/2 and +4. Some people try to build patterns of how these work, and they don't actually think about what they're doing here, and they end up building this wrong, and then everything is just a disaster after that. So you've got to get this part, and like people will just go like this, both negative, positive, negative, positive, positive. But it's not always like that. There's actually some cases where it's specifically not like that. And it's not always like positive and minus one on top of the other. Like it's not always like that. A lot of them are, but not always. So don't build patterns. Make sure you think about it. So this is going to be, and you could sub numbers in here to check. So -2 would be -4 plus 1, that's negative, and -2 minus 4, that's negative. What about 0? If I plug 0 in, x minus 4 is negative, but 2x plus 1 is positive. And if I sub 10 in, they're both positive. And 10 would represent this interval here. Anything bigger than 4 can represent the whole interval. So this one did work out like the other ones. So now I'm solving, this is when x is less than -1/2. And both of them are negative. So -2x plus 1 equals -x minus 4. This is when -1/2 is less than or equal to x less than 4. And 2x plus 1 is positive, but x minus 4 is negative. Ask questions if there's anything you don't understand, folks, because I said there's a whole bunch of like different types of questions, and I want to get to as many as we can. But if you don't understand why we're doing something we're doing, then it doesn't matter how many different cases we look at. Because the interpretation is all kind of the same from here on in. It's just, does the solution fit in the domain? There's a couple of quirky things that can come up. We saw one of them. So this is when they're both one of the quirky things was that when you got 0 equals 10 or 0x equals 10, right? So that's one of the strange things that can happen. You've seen that before in grade 10 in linear systems, that kind of stuff happening. And it means no solution to the system, right? But this is how we set it up, right there. From here on in, hopefully the algebra is pretty easy. Solving these is not supposed to be the part where we have a hard time. Interpreting your solution requires some thought. Setting it up requires quite a bit of work, and it's got to be done properly. Okay, so let's do this quickly. Negative 2x minus 1 equals negative x plus 4. X equals negative 5. Is that in our domain? It is. It's less than negative a half, so it's good. X equals 1. Is that in our domain? Yep. Between negative a half and 4? Yeah, 1's in there. Don't forget, you can check. Left side, right side, plug it in. See if it gives you the right answer. Don't plug it into this. Of course it's going to be an answer to that. You got to plug it in with the absolute values in there. So what if I put 1 in there? 1 minus 4 is negative 3, but the absolute value of negative 3 is 3. And 2 times 1 is 2 plus 1 is 3. So I got the absolute value of 3 equals the absolute value of negative 3. That's true. So that solution works. Next one. X equals negative 5. No. Extraneous. So I got 2 solutions again. Let's just see quickly what that looked like. If anybody has any questions, you can stop me and ask questions. So like there were the 2 solutions. See, this is the 2x plus 1. The 2x causes it to be steeper. So they cross twice, but you can see it's not going to cross again. All right, let's keep going. Okay, so we got to set up our intervals. Two x minus 2, what's the x-intercept involved there? 1. And what's the x-intercept of the other one? 3. So these ones are sort of up, backwards or upside down from how we saw them before. And below 1, so if I plug 0, 0 is less than 1, right? So 0 is in here. So if I plug 0 into both of these, they're both negative. What's a number inside this interval? How about 2? 2 times 2 is 4 minus 2, that's positive. So this one's going to be positive. And 2 minus 3 is negative, so this one's going to be negative. And then after 3, they're both going to be positive. If I put a big number in there, they're both positive. We really should, maybe if we have extra time, I'll make up a new example. There's one, I'm just going to throw this out there. If this was 3 minus x, because I don't think we actually have an example where it does this, but it's in the homework and we'll see it. We will see it eventually. If this was 3 minus x, this is a bit different. So you can't just go minus, minus, plus, minus, plus, plus. It's not how it works. And this is the particular case where things are different. Okay. So this is the case where x is less than 1. They're both negative, so negative x minus 3 equals negative 2x minus 2 minus 4. This is where 1 is less than or equal to x, which is less than 3. X greater than or equal to 3. And in this case, when I'm looking up here, which one's negative, which one's positive? So the x minus 3 is negative. But the 2x minus 2 is positive, so I leave it alone. Any questions? -3. Is that good? What happened this time? So is -5 in this domain? -5 less than 1, yep, that one's fine. Is 3 in this domain? Technically not, although you could have all of these be equal if you needed to. It's not going to change your answer. What you can't do is some people get a little too caught up on this. I don't want to make a big deal out of it. You can't have both of them be like this, because then we're not considering the solution at 3. So one of them has to include it. But if they both include it, it won't ever change our solution. So it's fine with me if you include them both. But technically, this one's not in there. But this one is. But we got the same solution twice. Why do you think that happened? So we've got two solutions that are fine. So therefore, x equals -5 and 3. And again, I don't want you to be caught by surprise when this happens, but look. So -5 just cuts through over there. But look what happened at 3. It cut through on the vertex. So that's why it gave me a solution for this and for this. Both sides of that absolute value. Does that make sense? So don't be surprised if that happens. It just means we've got one solution, but it happened at the vertex. But don't write it twice. Don't have another (3) at the end here. Questions? I'm going to keep going. We got lots of time. I've got a lot more examples here. But we've kind of, and so we're going to see this next one is sort of the last one that I really want to get to, so we're going to have extra time. So if anybody has questions or anything, we have time for that. If you want to try to set up this one, I would say go for it. You write out the arguments for both absolute value. We call these double absolute value equations. By the way, I don't know if I use that terminology yet, but we call them double absolute values. So this, you can see it's very different now that we've done a bunch. It's quite different from the other ones we were doing, right? Requires a different system. So you write both of them out, do your number line with your x-intercepts. Figure out where each one is positive and negative. You could visualize the graph for this, or I think what's probably better is testing values. So in -2, you pick anything in that interval, like -5 or -10, plug it in there. They both work out to be negative. That means I have to multiply them both by -1. That's how absolute value works. Remember why we're doing what we're doing all of this stuff in the first place. At first day, we talked about absolute values and how it has this quirky thing where if it's negative, it multiplies by -1. And if it's positive, we leave it alone. So we're figuring out where each of these is negative and where each is positive. And you have to go through this testing. You can't just do it based on a pattern. You might be able to do it quickly. You might find a way to cheat a little bit or something, some of you, but don't take it too lightly. As I said, there are some cases that are a little bit different. So then we highlight our intervals, 3 cases, kind of name them, state the domain of those cases, and then this one is where they're both negative. So my equation was, so I got negative x plus 2. And this is like, watch, put your pens down and watch. If you look at the original equation, it was minus x minus 1. So this is like negative x minus 1, which is going to make it positive. And it's equal to 3. Does that make sense? You could put it in brackets and put 2 negatives if you prefer, but it's going to ultimately make it positive. For this one, it's x plus 2 plus x minus 1 equals 3. And this one's x plus 2 minus x minus 1 equals 3. So this is negative x plus 2 plus x minus 1 equals 3. So I'm going to move, that should be minus 2. That's better. So I'm going to get 6 on this side and 0x, or 0 equals 6. Never true. 0x never equals 6. 0 does not equal 6. This is going to be 2x plus 1. 2x equals 2x equals 1. And this is going to be x minus x. So 2 plus 1 is 3. 0x plus 3 equals 3. 3 equals 3. This is always true. So what's happening here? Put your pencil down and watch. If I change this, like I said, you can include that point. If I change it to include it, this answer is fine, isn't it? But what is this saying? The fact that this is always true. What do you think it means? Zach? Very good. That's exactly what it means. It means starting at 1, because it includes that point, but this includes that point as well. Starting at 1, this always works for all values of x. So and remember, just like before, we always write it with the fewest number of solutions. So therefore, when x is greater than or equal to 1, I don't say x equal to 1 and x greater than 1. I say it as one statement. And watch the visual of this. There's the 2 of them. Oh, this is kind of interesting. So let me see if I can work this out. The blue one is the absolute value of x plus 2. And the orange one is the absolute value of x minus 1. And this question was, when I take x plus 2 minus x minus 1, when does it give me 3? Right? So when the blue minus the orange gives us 3. So that's negative 3 because I'm subtracting bigger from smaller. Again, don't worry too much if you don't fully follow this. So it's negative 3, negative 3, negative 3. All of a sudden it's changing. And in other words, the distance between these is 3, but I'm doing the lower one minus the one above it. So it's giving me a negative. But what happens when they cross paths? The distance between them starting at 1 becomes 3, and it's always 3. When I subtract the blue one minus the orange one, from here, starting at 1 forever, it will give me 3. Interesting. That's one way you could look at it. Let's see. This is the actual graph of that side. So when is it equal to 3? It's equal to negative 3 here, and then it changes, and it's positive 3 here. Like, who would have thought that's the graph of the left side of that equation? But it is. So that's another way of thinking about it. And this is another way of thinking about it if we change it up a little bit, and I'm not going to get into it too much, but again, you can see how this can have infinite solutions. These two graphs are crossing forever. So you got to know how to interpret these solutions, in other words. Any questions? We got a few more to do. Again, you can go ahead and try this one. That's like an x-intercept of 0, right? When x is 0, that's 0. That's going to flip. Okay, and I've got my 3 cases. Okay, so I've got my 3 solutions here. And I'm going to check out and see what happens. When I got x equals -1 here. So this is true. This is true when x equals -1. But is -1 in this interval? No. No good. Not in the interval. What about -3? Is x equals -3? Is it in that interval? It is not. And what about -9? Is it in that interval? X is greater than or equal to 0? No. Therefore, no solution. And what does this one look like? It looks like that. They never cross. If you think about the graphs, this is the 2x plus 5 plus 4, so it's gone up 4. And it's steeper, and they're never going to cross. I'm going to skip the last 2 examples. I will post the solutions online if you want to look at them, but they work like this. Let me see if I can get this right. One of them is that graph instead. Yep. So this one has one solution. So like I change it a little bit. This is the equation down here. 2x plus absolute value of 2x plus 5 plus 4 equals absolute value of 2x versus the one that we just did, what was the absolute value of 1x. Okay, one solution. And then I believe the other one is what if it's the absolute value of 2x plus 5 minus 4? Well, then I end up with 2 solutions. So like I just have these different cases. Obviously, change something a little bit, it can change things, but you might get no solutions, you might get 1, you might get 2. We have all these different possibilities. You might get infinite. All kinds of things can happen.